Hello, just testing the microphone. Testing some more. 1, 2, 3. Hello, RetroCludge. Nice, thank you. All right, let's start this thing. So this stream will be sort of filled with random stuff around the Nintendo Game & Watch. There are two things I really want to fix today, and that is, first of all, getting a 128 megabit flash memory to work with the firmware we have. And then I also want to fix the audio buffering issues we have in the emulators, because currently it doesn't sound that nice. It sounds okay, but it could be better. So yeah, let's get started. So the project I'm working in right now is the Game & Watch Flash Loader. The purpose of this code is to set up memory mapped access to the external Spi Flash, and also to be able to erase and flash that memory, like program it. And I did some quick bring up yesterday and I had some issues, so today I will try to fix those issues. So yeah, let's just get started, I guess. Just gonna connect some stuff here. First of all, so this is an ST-Link, a debugger for the ARM microcontroller. Just gonna connect it. And tape it down. So then we need some power. Yeah, that doesn't look very good. So Okay, so what I'm doing now is to add a make target to the make file to make it more convenient. Are you a German living in Sweden? Skidra Ninja. No, I'm Swedish. I just have a German sounding name, and I live in Sweden. So yeah, what I'm doing here is I'm setting up a make target to be able to flash it easily. So we take the, let's see if we need to do this. Yeah, we extract the flash from the binary and then we program it. Yeah, and this one is basically the same thing, but it will, instead of executing OpenOCD, it will just send the command to the already running OpenOCD session. This one won't be needed. This is to start the GDB session using make. No, he does not. All right, so now we have flashed the target and we are in the reset handler. So now we are able to step and break in the code. And it works. Hello, Pepin. Yeah, so what we should do now is to try to make the memory mapping work and the flash configuration. So we can just go to the initialization code and check it out. So what are we doing here? We're enabling write to the flash. Actually, we're resetting it first. And I think these commands are all fine because they're the same across memories. There we go. If you use fish shell, try my make tool. Ah, nice. All right, I need to set up this project a little bit better. I haven't done anything in this. So let's go to the make file again and look for definitions. We have these two definitions. We can add those to the editor. That way the editor will be able to find stuff easily. Yeah, now it doesn't complain. So what does reset make? What does it do? It set up a command structure where it sends the instruction OX66. And the way the API works is that you set up a command and then you set up the number of bytes you want to send, which is 0 in this case, I think. And then you send, yeah, and that's basically it. So if you need to send data afterwards, you can do that by using this API, the OSPI transmit command. It's a little bit confusing, but that's how it works. So for the single instruction commands, it's pretty straightforward. You just set the instruction, and you call the command function, and that's it. And in this case, we want to send enable reset, and then the actual reset with a delay in between. So let me just open up the datasheet. I already forgot the name of the flash chip, but I have it here. Just a second. All right, so this is the flash we're using, and yeah, here it talks about how reset works. So yeah, you should send 66, wait a little bit, toggle the chip enable pin, and then send 99. And that's what we're doing. 66 first and then 99. So that part is fine. And that also works with this bigger flash chip. Then what? Then we do the write enable. So what we could actually do is to just add a infinite loop and just get stuck here. And so we can try out the flash read. So in order to do that, let's check out what happens in the configuration. So let's see here. Maybe we don't actually do that in this code. Oh wow, I already got some spam. Nice. Maybe I should make somebody up in the chat. How do I kick people? Yeah, as you can tell, I'm not very used to stream. Wow, how much spam do I get? Damn it. If anyone wants to become a mod, let me know. Would be nice. Damn it. Anyway, let's get back to the code. That was distracting. Okay, cool. Nice to meet you, Mount True Guitar. Ah, right. Hi, Timon. Nice to see you here. Like, I'm a super noob at streaming, so yeah, I think I made you a mod now, Timon. So feel free to kick and ban people as you wish. I trust you. All right, so let's get back to the code. So the way we do it in the emulator is that we, in the main function, we have this nice little function called flash memory map. And what this does is that it sets up a command for, let's see here, yeah, for the read configuration. So this sets up like a quad read, quad address, and so on. And when this is sent to the to the HAL, this enables memory mapped reads, which is super convenient. So what we can do is we can just copy this and improve it. All of this code is sort of ugly CTF code where we have just bashed our heads against the keyboard as fast as possible until something works. So yeah, if it looks like crap, it is because it is. So sorry for that. All right. Cool. Yeah, okay. So first we reset the chip, and then let's maybe there is actually some code error already. Okay, right, there is already the flash memory map here, but we don't actually call it. So let's do that. And we can call the function something nicer. Let's just double check that it's not being used. Right. Yeah, okay. So again, what this function does is it sets up the command structure for reads and writes to the memory. So in this case, I think we should just start off with a single Spi mode. So we have something basic that works, just to verify that it actually works. So we go to the datasheet and we look up the various commands. If I don't misremember, it should be like OB or something. Right, fast read operation, OBH. Yes, that's what we want to do. And this is the waveform. So we send the OB 8 bits and then a 3-byte address. And then dummy cycle for 1 full byte. So that is 8 cycles, right? 1, 2, 3, 4, 5, 6, 7, 8. Yep. And then you get the data. So let's do that. So we change this to OB. And that is the fast read. And then it's 1 line instead of 4 lines. And no alternate bytes. So I'm still a little bit confused to what this actually means, but it seems to be if you need to send some extra byte after the instruction, but before the address, you can do that here. So maybe if you have some dual command, like commands that are 2 bytes, you can do that. I don't think any flash chip uses that, but maybe something else does. I don't know. Oh, okay, Okninja. I'm just gonna double check. Yeah, I am recording this. I'm gonna put it on YouTube later, I guess. And it will be completely unedited and horrible. But anyway, you can just skip if something gets boring. All right, so let's continue. We want the data to be 1 line and address 24 bits. Yeah, let's just clean up this mess. Dummy cycles 8 because it's 1 full byte, right? Let's just clean up this a little bit. I think the data should be 0 because that gets filled in by the memory map thing. Okay, yeah, we can move this down. So what I found out earlier was that it seems that memory mapped mode only seems to work if you have both a read and write configured. We can double check that if that is still the case. I don't know. It seems kind of weird that you need to have a write configuration because some flash you just want to be able to read, so it doesn't really make sense to me. Anyway, we don't need to change these things because we have already initialized that already here. So what we do here is we enable it. So that's it. And let's comment this out for now, just to double check. And then this is what actually enables the memory map mode, I think. It's still kind of unclear to me, but it sets some sort of timeout. Yeah, it's for how long the chip select is being held low. So the reason why you want this to be long is that if you make a sequential read, you don't want to send the address again and again and again. And with the timeout that is long, or disabled even, it will just stay low and wait for you to do your next read. So that's nice. So let's keep it like this. Okay, I think we're ready to try this. So we flash it, and we open the debugger. It seems to get stuck somewhere. Okay, so it actually failed. So as you can see in the call stack, we entered the error handler, which we came there because of the memory map mode. So it actually failed on line 179. So for some reason, this is not HAL okay. So let's step inside here and check it out. So I set a breakpoint. I reset the target. I continue execution. So now we run the code until we hit this point. So let's play along, see what's going on. So, oh, okay. So it failed really early. So for some reason our state is OX14. Okay, so we are in this state. Read command configuration done, not the right configuration. Okay. So if we do a right configuration, okay. So this is actually explaining the stuff, the problem I had before. So this indicates that you need to actually configure both a read and write in order for it to work. So, well, now we have an answer. That's good. That's better than just guessing. So in order to be safe, let's just reuse the read command for write, which means that if you write with the memory mapped mode, it will just not change anything. So yeah, let's just not do anything. Cool. So let's try this one more time. Here we go. And this time the LCD, I don't know if you can see this on the screen. I think you can do it on the video. The LCD is white, which means that it's not blinking. Because if it is blinking, that means that we have hit the error handler. All right, so let's run. And now we can see that we actually ended up in main on line 121, which is this. So we have been able to execute all the way here. So now it's time to check out what's on the flash. So now the flash is memory mapped to OX90 and then a bunch of the zeros. So yeah, this doesn't look very good. This looks like the flash is erased, which might be the case actually. Honestly, I have a bad memory. I was messing around with this yesterday and I thought I had it programmed with something, but it doesn't look completely wrong. Like if it is erased, then this is the expected, yeah, this is what we should see. So what's your ultimate goal? What's your ultimate goal to achieve with the Game & Watch? I honestly don't know. I don't have a goal per se. Like something that I would like to do is to run a C64 emulator. That would be really cool. I'm not sure if Vice is able to run on such a low power device, but I want to try. That would be really, really cool. Yeah, we'll see about that later, perhaps. So, I mean, there's the obvious thing that you might want to do, but I'm not personally that interested in it, and that is to have like multiple emulators and a bunch of ROMs on the storage. That is probably I guess a lot of people want to have that, but personally, I don't care too much about that. But yeah, I'm happy to provide like a integration with the various emulators and then people can take it from there basically. But yeah, for now, I just want to make the Flash work. So yeah, so let's do that. So hey, so what I'm doing now is I'm configuring the flashes. I'm using the 128 megabit flash, and I'm just starting in easy mode, doing the Spi mode read, and it seems to be working. Are you reading from external flash? Yes, it is. If so, how is it connected to the STM32H? Yes, that's correct. And if you look at my camera, I have this extremely hacky mod um, where I am actually, let's see if this works. I'm gonna turn it around. Yeah, let's see if the camera can focus. Like I soldered the wires to an adapter so I can remove the flash easily and program it. So that's how I'm able to test it and program it with an external programmer easily. Let's fix this again. So replacing the default factory flash. Yeah, that is what I'm doing right now. So what I'm doing now is I'm using OpenOCD that talks to the ST-Link, that talks to the STM over SWD, and then I'm using GDB as a debugger to to debug. Do you plan on making a guide on how to get started with hacking a Game & Watch? Yeah, stack smashing. Maybe you can answer this in the chat. I don't know really how much I can say right now. But yeah, I guess something is coming. Yeah, so it looks like this seems to work. So let's try to fix the flashing. So in order to do that, we want to send the write enable command. Don't know why this isn't working. And what does that do? Yeah, it sends the 06 command, which is the same on this chip as well. Yeah, write enable. And then it should send the chip erase, right? And because the flash is so big, this might actually take a while to do. But for now, let's just not do the chip erase. Yeah, this will be fine. And then we need to adapt this command to be single SPI mode. And it is actually that already, right? The O2 command, as you can see here. Yeah, so this is like a cheat sheet, pretty convenient. You can see that in 24-bit mode, you only need to send 3 bytes of address and then the payload, 256 bytes. Or actually, is this QPI? This is a little bit confusing. So yeah, here it seems to be SPI mode, only SI and SO. But here it's the same instruction, but okay. Right. So this Flash seems to have different modes that you need to select. Like you enter Spi mode or you enter SPI mode. I think it boots in SPI mode. So I think this should actually work as is. So let's just try it out. So I'm just gonna steal some ugly code. Here we go. So I'm just gonna write a counter to a file, basically. Oh, there we go. So this is how it's supposed to look. Yeah, 0, 1, 2, in little endian. So yeah, let's just do this. So we're gonna program this now. So what this script does, flash.sh, oops. Yeah, so it loads the binary into RAM, like so, and then it programs the firmware and waits. So what we can see here on the screen is that it's fully on, so it's busy writing, I think. Maybe I didn't actually build the firmware. Oops. Yeah, let's make one more time and run it again. It takes a while to upload. Okay, it flashed pretty fast. Oh, rapid blinking. Ouch. Let's see what happened. So, write enable failed. That's odd. Why would it do that? So this is the first thing we did after enabling the memory map mode. Could it be that you're only allowed to do this when you're done sending manual commands? I'm gonna guess that and just disable the reading for now. And let's do it again. Right, it's uploading. It always takes a while. With the more fancy debugger, like a JLink, you can, yeah, this will be much faster. Okay, it is not blinking, but it's also not blinking fast. So this probably means that it's busy programming, because that might take a while. Yeah, if I remember correctly, I actually, let's see here. Yeah, okay, it's actually blinking slowly now. So that means that it succeeded. So that's cool. Alt. I'm gonna do something illegal here. I'm gonna call a function from the debugger because I'm too lazy. So let's see if this actually works. I almost never do this, but I just want to try it out. Okay, damn it, it was optimized away. Too bad. Let's just build it and get stuck here, yeah. So now I'm uploading a new firmware where we enable the memory map mode and stay there. So let's do that. Okay, this is bad. So it's actually not writing it. So that's too bad. Which means that it's time to connect a logic analyzer to see what the heck is going on. Why isn't stuff working the way we're expecting it to? So I'm using a Sali logic, or however you pronounce it, and it has an insanely bright LED, so I had to tape it. Some fancy probes. And yeah, let's set this up. So since we're operating in a single SPI mode and not quad SPI mode, I'm just gonna connect the 4 pins. Yeah. All right. I guess the easiest way to do this is to connect the clips first and then turn it around. Okay. So I did like this, where I connected the probes onto the adapter, like so. And I'm gonna connect it. Okay, good enough, I think. Just need to connect the cable as well to my computer. Alright, now it's connected. Let's see if it works. Yeah, seems to work. Cool. Just gonna lower the sample rate or sampling duration. Alright, I need to remap the SPI pins, so let's do that. So you can see this is obviously the clock. And then the chip enable is channel 3, MOSI channel 2, it's here. Ah, right. Yeah, okay, here you can, it's maybe a little bit hard to read. I don't know how to increase the font size in this program. Maybe it's possible. No. If anyone in the chat knows how to increase the font size, just let me know and I will do it. But if not, I'm sorry, it is what it is. Anyway, what we can see here is that we are sending OX OB and then 1, 2, 3 zeros and then OX88 and then 0, 0, 0, 0. So that doesn't look good at all. Why are we sending OX88? That doesn't make any sense. Because we should not do that. We are trying to read the first memory mapped region, and or actually let's just do like this. It's one single read, nothing else. Okay, now that is probably cached. So let's do like this. Break it. Do like this. Okay. Now this is what happens when we ask for one word. So for some reason we get this 88. That is weird. So we're running the flash at 70 megahertz, so that's pretty fast for my janky wires. So let's change that. So let's increase the prescaler from 1 to 4. So what this does is the clock that we're using for the SPI flash, we are dividing that with 4. So let's flash it and see what happens. If you don't want something to show up in the video in the chat, I'm sorry. If it's written, it's already written, but you can write a few lines to hide it, I guess. Okay, back in business. Let's see what happens. Okay, so this looks cleaner, but we still see the OX88, which doesn't make any sense. So maybe we're missing something. 8 dummy cycles. I don't know. We could do it like this, I guess. Or just to verify that these alternate bytes are not sent, let's just set it to some known value. This is what's confusing me quite a bit, actually. Yeah, so let's do like this, and do a full capture. So gonna sample for 1 full second and continue. So what do we get? We get 2 commands. The first command is OX66, the other one is OX99, nothing else. So that's good. That means that we're not getting any magical accidental reads. So what we can do here is that we can, let's do like this. Yeah, like so. And then I'm just going to copy some code. So because this system doesn't have a UART, which is extremely annoying, we need to make do without it. And one way to do that is to have a log buffer that simply hooks into the write function, so that when you use printf and putS and similar, it will simply write whatever you're printing into the log buffer. And then from the debugger, we can print this. So let's do that. Right. So here we go. Okay, it's not building because I'm stupid, probably. Yep. So I also need the log index. There we go. So GDB has a fun command called printf, actually, where you can use formatted strings. That is useful for when you are... Oh, right. Yeah, there you go. That is useful when you want to print strings that contain the new line character. Because if you just use print, you get something that looks like this, which is really annoying if you have a big print buffer. So that's kind of useful. I keep learning things about GDB all the time. It is quite a big program. But anyway, this is a nice trick. I can definitely recommend it. Okay, so we are reading a bunch of FF, which is probably correct, I guess, but yeah, okay. So now we're back in the logic analyzer. So let's do a full capture. On, reset, alt, and then continue. And we can see that we get the enable reset, and then the OXEB, and then 1, 2, 3 lines with the address, and then 1 byte with dummy bits. Yeah, dummy cycles. Yeah, that's what it is. Okay, of course. And then here we get the actual data. And the data is a bunch of FF, which is probably also correct because this is an erased chip. So cool. Now the question is, when we write to it, why doesn't that work? So let's just remove this whole code, which is really useful, but we don't want it right now. And then we're gonna do write enable and program, and we want to program it with like so, yep. And then let's write a few values. RAM 0. Okay, this is probably good, right? So let's just mem set RAM with yeah, a bunch of A's. That's nice. All right, or actually, no, this will be fine. Yep. That's not good. Yeah, do it like this. Yeah, that's correct. So let's just program one page. Buffer size, number of bytes. Yeah. Yeah, this will be perfect. Cool. Oh, yeah, the trace pin, that would have been useful. Yeah, for profiling, that's really useful. But I think, let's actually check that. So I'm just gonna check if the pin is muxed with something else. How do you actually find that pin? So I'm looking for the SWD or SWO pin for the ITM trace. So if I'm not mistaken, I always get confused on this. There we go, trace of debug. External trigger, JTAG serial error. Yeah, serial error. I think. So that's the clock and that's the IO. But where is the ITM pin? I guess we can look it up in the pin 55. Thanks. Okay, so it's used for some GPIO PD8. 89. Okay, 89. Oops. Okay, but this is good news. It looks like it's actually free, this pin. It doesn't seem to be used. So I guess you can solder a pin to it and use it. So that's cool. Nice. Okay, but back to this. Let's see if we can program one full 256 page with this data and OX41 and the rest of the data, and then just get stuck there. And then read it afterwards. Yeah, let's do that. So write enable program. All right, maybe add a delay as well. Delays are good. I've learned the hard way. Yeah, this will be perfect. Cool. So let's flash it. And then alt debug printf. Okay, this time it looks different. So it seems that we were actually successful in writing something, but this looks a little bit garbled. Right. I see the problem. Though. So maybe it's actually working because it takes one byte at a time. The LSB, the second one. Okay, maybe this is actually done. So now we have a single wire Spi mode for the big flash. Cool. So the question is, why doesn't it work with the old code? Maybe, I don't know, because this looks promising. Maybe it's the chip erase that doesn't finish. Right, that could be it. So the current solution is a little bit naive. It will call chip erase and just sleep. We can improve that. Seconding the question about the flash chip. Has it been installed yet? I have two set on my desk. I can solder, gonna be interesting. Yes, so this chip right here is 128 megabit. It is literally this chip, which is not the same series. It's not the same vendor or manufacturer as the original chip. So it behaves a little bit differently, which is why I'm using single wire mode right now, just to be able to verify that yes, it does indeed work. So now that we know that it actually works, we can comment this out and enable the old code again. So what does it do? We reset the chip, we do write enable, we do chip erase, and then we program it, and then we blink. Nice. So let's improve the chip erase, because we can improve this a little bit. So instead of this beautiful hack, which is very effective, let's remove that, and instead okay, maybe let's just be lazy. We want to do a read instead. So we want to read the status register. So how do we read the status register? Well, we need to set up a read command. So let's do a helper function for that. So we want to read I guess like this. So we send 1 byte with an instruction, and then we get some bytes back. Yeah, that would be nice. Let's do that. So we do it like this, and this will be the common configuration. 1, 8, address none. And instead of data mode, data none, here we're gonna use this. No dummy cycles, but we need to set the number of bytes. Yes. Yeah. So first we send the command. This will literally send this part. And then we want to send a payload afterwards, which will be just a bunch of zeros where we clock out the result. So, and instead of calling transmit, we will call receive. And let's look at the function. It takes a pointer and a timeout. Cool. So the pointer in this case is data, and the length is already configured here. And yeah, timeout default, that's perfect. Yeah, that's it. Cool. So let's do that. So we are reading bytes for this one, and we should have buffer. Let's just have 32 bytes because that's good to have. Alright, the instruction as well. I don't know how long it is. Let's check it out. Status register. Read status register. It's 05. Okay. And how does that work? It is only one single byte. Cool. So here we read. So we ask for the status register. We want to store the result in buff, and it should be 1 byte long. And then we set done equals buff 0, and then we need to check which bit is what we're looking for. And I don't remember which one it is, so we need to check up the status register. Okay, write in progress bit. That's bit 0. Okay, I guess that's it. So if bit 0 is set, we are still writing. So it's done when that is 0. Maybe this is confusing to read. So let's do that like this instead. So when bit 0 is not set, we are done. And then we exit the loop. And then here we do the hull delay with like 100 milliseconds perhaps. Cool. So now the chip erase should ideally just take as long time as it actually should, and not longer. And after that, we return execution here. We can actually remove this. And then we will program it with the contents of the RAM. And then the flashing will be done, and we will be blinking. Perfect. Let's try it. Cool. So make. Then I'm going to use the flash helper script. Let's just double check one thing. Yeah, so the counter.raw is a fully 1 megabyte flash image that we made it before, but maybe you forgot about it, but it looks like this. So it's little endian counter 0, 1, 2, 3, 4, 5, and so on. Perfect. So let's flash it. All right, it's still uploading the image to RAM, I think. Okay. I think it's doing stuff. We can actually look at the sniffer here to see what's happening. So yeah, it's definitely doing stuff. Okay, it's querying the status register, and you can see that it is actually getting OX3 back, which means that the two LSBs are set, which means that write in progress and write enable latch are both set. And now it's actually done. So now it's blinking, as you can see. Let's attach a debugger, and actually I will not be able to verify this because I didn't enable the memory mapped stuff. So I should do that. So let's enable this and flash it again. Yeah, this should work. And then debug. Okay, this looks promising. Okay, look at this. 0, 1, 2, 3, 4, 5. So this is the proof that it is working. Or it seems to work. So in order to actually prove that it's working correctly, we should do a full dump. And in order to do that, we can use the dump image command in OpenOCD. And let's call this flash dump at 1.bin OX90, and then size. I always forget how many zeros it is for megabyte, but I think it's 5. Let's go. Yeah, exactly. It's always nice to have a Python console somewhere to do some calcs. Nice. And again, I'm running this flash now at a very low speed. Okay, now it's done. Cool. Let's diff. They are identical. Perfect. This means that this is actually working. Perfect. Nice. So what can we do now? We can improve this and make it to use quad SPI instead of single SPI. So I don't know, maybe I should clean this up and commit it, because this is kind of nice to have. Commit and push, yeah. Yeah, but it kind of sucks, because this makes it worse for the small flash. Then I can test whether it restores the original form or not. Yeah. Are you running with a big flash as well? All right. Cool. There's a bug in restoring the original flash image currently. Okay, that worries me. Why? That's weird. Because I haven't really done anything that magic here. I've just changed some commands basically, and I added this while loop where we actually wait for the status register to, yeah, wait for this register to, yeah, cool. Oh, we should, let me just add a git ignore. Yeah, much better. Yeah, let me just rework this a little bit. this should be it, right? Can you save the stream so I can continue watching in the morning? Yes, I can, and I will. I'm already recording it, so don't worry about that. Okay, so I believe this should be enough for me to push it. I don't like to push things that are really broken. Slightly broken is always fine. Okay. Let's see if it builds. Yes. Okay, I'm gonna commit this now. Okay. Oh. 1 second. Ah, right. I guess I'll just make a pull request for now. Okay. Yeah, if you can add that, that would be super sweet. Nice. Yeah, no, so the next step will be to, what is this? To add proper quad support, and then I can also improve it to program in quad, because right now we're programming in single Spi mode. Thanks. I will press the accept button, and there we go. Nice. Okay. Cool. What do you want to do now then? Proper quad mode. Yes, quad is faster, I guess. Yeah, it's 4 times faster, and not only that, but it no, it's 4 times faster. Yeah. The thing is, I had to screw down the prescaler here to 4. But I blame that on my setup. Like on a proper device where the chip is soldered down properly, it will probably work at the full speed. I don't see why not, because this flash is actually faster. It's 166 megahertz compatible. So, and I think the old one is only went up to like 104 or something. So yeah, this is pretty fast. You can overclock your flash. It even works in DDR mode. Actually, DDR mode might be safer to use for what's it called again? Signal integrity issues, because yeah, the frequency is lower. Yeah, whatever. I don't want to mess with DDR. That's gonna be a headache to get that right, because usually you have problems with the phase. Might be a little bit of a problem. Okay, cool. Let's get quad working again. So let's start with the easy mode. Which is to say we want the memory mapped mode to work with quad mode. So we look at the datasheet. Wasn't it EBH? Yeah, fast read quad IO operation. So let's read this for a bit. Yeah. Right, so this is a status register, probably bank address register. Yeah, we want this to stay at 0 because 1 megabyte is conveniently 24 bits, so we're at the maximum. Are you not waiting for whip bit in status register of the programming page? Oh, that's a good point. Thank you, Corgo, or however you pronounce it, Corgeo. Oh. Anyway, thank you very much. I did not realize that. Good catch. So let's do that. Let's just copy this little while loop that we had somewhere. Yeah, so this one we can just copy and paste to this one. So for each page we program, we wait until it's actually done. So yeah, maybe we can rewrite this a little bit better. So we can just let's do it like this. Actually, this is gonna be, yeah, maybe. Okay, this should work, right? We have a status, write into status, and then we check if LSB is set, and then we loop. Yeah, this should work. Cool. So let's do this. There we go. So before we continue, then we can remove all the sleeps. Or maybe not all of them, but a few of them. This one. Yeah. So let's go to the count, make a new one. Or actually, I can just read. So now we have 1 megabyte of random data. And so let's just double check. We should comment this out. Right, so we are resetting, write enable, chip erase, program one page, blink. Or actually program the whole thing and blink. Yeah, and after this we can actually do this. That way I can dump the RAM immediately, or the flash, yeah. So yeah, this will be interesting to see. Sorry for being a little bit inactive in the chat, I'm not that good at this. So, are you connected with SWD to upload the firmware and to Flash in order to verify the write? Yeah, that's correct. This is using only SWD. Also for QSPI, you need to set the QE bit in the status register. Yeah, thank you. And I will get to that in a moment. Don't get hopes up too high. Real fun will begin with soldering proper SD card mount in place of flash. Yeah, the problem with that, JTH, is that you will need to modify the case in order to expose the SD card, which is less than ideal, but possible. Okay, let's see what we have. Oh, this didn't work at all. Oh, right, because I'm stupid. Don't be stupid. So I had forgotten that I had a 1 on the memory map mode, which means that it enters the QSPI mode-ish without setting the QE bit. So that's why it didn't work. So let's flash this one more time and make debug. And yeah, okay, now we get some values. Cool. Question is, are they correct? So let's make another dump. And then we're gonna diff this with the binary that we uploaded. So this is just gonna take a few seconds. But yeah, this is pretty much the process when you develop. It's not really straightforward. It always takes a little bit of time. Sometimes it doesn't really work, and so on. Flash dump 2. Ouch, this is not good. Why do they differ? So let's open up meld, I guess. No. Binwalk actually had a really nice tool that I didn't know about. Okay, this does not look good at all. So here it seems like a whole page is not flashed. So the star here means that the values are the same from 0 to 8200. And then it differs. Oh, this is not good at all. So maybe I'm being too fast. Maybe I forgot something. Binwalk-w-i. Yes, exactly. It's perfect. Thank you. You taught me that, and I'm really happy I didn't know about it. It's super useful. It's only a little bit slow, but yeah, it's okay. Let's see. Yeah, case 3D printers. Yeah, you're not wrong, but the original case is kind of nice. I think it's like injection molded and so on. Like it has this nice finish. It's hard to 3D print that. Okay, so why do we get this? Why aren't these pages programmed? That's weird. 8200. Isn't the case one of the biggest reasons to play with this? Yeah, you're right. You're actually right. Because it looks so nice. Okay. Okay, so what if I add back the delay and actually increase it? I really don't like this. But I don't understand what's going on. So let's do like that. And actually, let's create a new random file so that they are unique. Because with this, it's really important that you look at different things, because otherwise you might actually see the programmed bits from the previous run and so on. So that can be extremely confusing. Flashing 1 megabyte takes some time. Has program process even finished? Well, I would imagine that... Oh, maybe I was too fast. Oh, maybe I was stupid again. Yeah, I should wait until the screen blinks. Maybe it didn't blink. Oh, yeah. You're probably right. So let's be patient and wait for the screen to blink. Yep, let's just wait. Yeah, okay. This really takes some time because it's still on. Yeah, and I run this in single SPI mode in a quarter of the speed. Yeah, remember this prescaler. So this should actually be a 16th of the speed of the original one. So yeah, you're probably right. Yeah, I didn't think about that at all. But now we actually... okay, now it's actually going to be super slow because I added this sleep as well. But yeah, then we can remove this. Definitely. But since I have this... Oh, actually, oh my god. I should not do like this. I completely forgot about this 100 millisecond sleep. Holy shit. Let's... I don't know. How much do you want to sleep though? 1 millisecond? Is it... Okay, for you folks who have experience with this, is it bad to spam the SPI chip with commands? Like, would that make stuff slower? Or should I keep a delay here? I honestly don't know. What's the best way? I guess we can remove it because there's no real reason. Like, we don't do anything with the firmware. We don't need to care about, not hogging the system and so on. You can query it constantly. Yeah, then just let's do that. Cool. And prescaler, let's increase it to 2 at least. Yeah, this will probably be fine. And then I removed this sleep already. Yeah, so this is a completely sleepless solution now. Let's go to main and see what we're doing. Okay, write enable, chip erase, program the whole thing, enable, and blink. Perfect. Yeah, let's do this. Make and flash. Oh, I was stupid again. I should use a different... a new random file, because otherwise, Oh, this is not good. Okay, here we go. Man, flash chips are magic. Yeah. And it's also kind of funny because you basically get the data almost immediately. You get it 6 clock cycles later. Page. Maximum 0.8 milliseconds according to the datasheet. Okay, nice. Okay, then I guess our solution now is optimal. Like, we cannot do it better. Yeah, if we had a UART, that would... Oh, it's already done. Holy shit, that was fast. So the question is it really? So let's do a flash dump again. This takes a while because of the slow debugger I have. Okay, it's done. So let's diff. Yay! So this means that it works. With the flag check, I was now able to restore original firmware. Yeah, nice, nice. Perfect. I will commit this as well, because this actually improves stuff. Yeah, perfect. All right, it's pushed. Okay, so now we can move on to quad. So I think the easiest way, the way with less hassle, is to start with read. And to do that, we will do it like this. And bump this to 1. And this will probably not work because the quad enable bit needs to be set. Now it was in the chat a few lines ago. QE. Okay. So how do we actually write to the status register? The search in Chrome is a little bit bad. Okay, write status register operation. Yes, this is what we want to do. So I guess what we want to do is to read it first, flip the bit, and then write it back. So let's go to I don't know what the cleanest way, maybe in here, yeah. If quad mode, we should do we should do it like this. And then we should enable the bit for quad enable, whatever that is. And then we should send it. Maybe I need a helper function for that. Yeah, let's do a helper function for writing. So here is read, and then here's write. Instruction, date and length. Yeah, that's basically it, right? Maybe we should have a dummy cycles as well. data. Status 1. Cool. So what is the QE bit? Was this nice? Okay, so it's bit 6. Right. Just double checking. It's always a little bit confusing when you do like this. Like, is this the 5th bit? No, it's actually the 6th. Or actually, it's the, right. So I should actually do this. Okay, this looks good. Does it say if you can write all of the registers? Ah, right. Read, write. Yeah, okay, let's do this. Okay, this doesn't look good. So I'm just getting 888888888 for some reason. So that's bad. Maybe if I step here, okay. So I think your ORing status with 0. Oh, yeah, okay, but that should be fine. But yeah, you're correct. I was blinded by. What am I actually doing here? Oh, I am stupid. Oh my god, this should be this. This is the instruction, though. Thank you for the help. Let's debug again. Okay, it still doesn't work. Why not? Status. Okay, so let's break and step. So status is 0. Does that make sense? Write in progress is 0. Write enable. Yeah, it's probably 0 because we haven't enabled it yet. Block protection 0. Quad enable 0. Status register write disable. 0 is not write protected. Okay, so 0 is actually good. And then we OR it, and now it's OX40. Does it make sense? 1 shift by 6. So 1 shift by 0, 1, 2, 3, 4, 5, 6. Yes, that makes sense. So, did I mess up this function perhaps? Oh, is it time for spam again? Who wants to be a mod? Raise your hand. Yeah, I did that. I forgot to do that before. Thanks for helping out. I didn't realize that it was that you get so much spam. It's a little bit distracting. Okay, cool. So we send this status register. Does it actually work, or did I mess it up? Dummy cycles, number of data. Yeah, I mean, this makes... Oh, right, I have a logic analyzer. So I sometimes forget I have this thing hooked up. So let's check out what's going on. Come on, reset, halt, and continue. Oh, no, delete. One more time. There we go. So we can see we set 66, enable reset, do the actual reset, then the status register get, the OX05, and the return value is 0. Then we send, yeah, we send the command 1 with the payload OX40. So this looks fine, right? Command or instruction OX01 with the data OX40. Or did I? This is the right bit, right? This would be OX80, and we don't want to set that. This is what we want to set. So this is correct. Or did I miss something in the actual write status register command? No, there are no dummy cycles. Oh, right. When we are in quad mode, we need to send the instruction in quad mode as well, I think. That could be what's happening. So we need to change this one into this so that everything is in quad mode. Instruction, address, and data. And after this, everything has to be in quad mode until you power cycle the device, I think. Oh, this might be... Oh, this is confusing, I think. How long does that persist? When you set the quad mode, does it persist forever? Or until the next reboot? Because until the next chip select, it wouldn't make sense for it to reset. So let's see what happens. Make flash. Make debug. So no, didn't work either. And if we look what's going on. Alright, it's just sending clocks because that's how it works. How do you tell GDB to like stop continuing? Maybe like this. No, this is stupid. Okay, let's do like this. Okay, so this is what's going on. We do the chip enable toggling. We send OX40. Oh, right, because it's in quad mode, I can't really see it. I need to connect the extra 2 bits. But even so, I don't understand why we only get zeros. That doesn't really make sense. Yeah, and thanks for everyone who's following. I'm sorry I haven't really noticed, but yeah, it is. Right. Yeah, so this is the sort of not so exciting part of programming, I guess. Stuff doesn't really work. It should work. trying to figure out why, banging your head against the wall, and so on. I guess we can, just for safety, turn down the prescaler. Yeah, I agree. But I guess for people watching the stream and so on, maybe it's boring. Or maybe not. I don't know. Look at me making all the mistakes you can never do. Yeah, perhaps. Okay, so the first read. Oh, this doesn't look good. I think I have some signal integrity issues still, but I mean, I turned down the prescaler. Should be fine. Yeah, maybe I shouldn't care too much about that. Okay, so let's just go through the code from beginning and see if I messed something up. So we reset the chip. That might not be. Stack smashing. Do you remember if there is a GPIO to the flash? Like the power that you can power cycle the flash using GPIOs? Quad commands are necessary only after entering QPI mode. You should send initial EB command in 1-bit mode. Yeah, okay. There is, nice. Yeah, because what I'm a little bit worried about is that maybe the quad mode is persistent. Let's figure that out from the datasheet. Oh, this is kind of interesting. So, is the number of dummy cycles dependent on the frequency? Can you configure that? Because that would be kind of important. Like, what if you... Okay, yeah, EB command is rather special. Yeah. Okay, because according to this schematic or trace or whatever you call it, the instruction is on the single line. Let's spend some time reading this text. I will be quiet for a while. Okay, it doesn't really say anything about the instruction. So it seems that the instruction is supposed to be on one single line. But I need to read about the quad mode. Because on the other flash chip we didn't have to do that. It just magically worked without any setup. So yeah. Is this what we're doing? Enter quad peripheral interface mode? No, we are not. That is not the same thing. Because what I'm doing is actually I'm setting the status register. I'm enabling quad enable like this. But there is a different command called QPI enable and disable. This, on the other hand, all instructions thereafter will be 4-bit multiplexed input-output until a power cycle or exit QPI instruction is sent to the device. That's interesting. So I guess if I'm using this, then I can use the 4-bit instructions. So let's do that instead. But the problem with this is that you need to power cycle the device in order to leave it. QPI makes every transaction 4-bit wide. Yeah, I'm gonna try the QPI en command. See what happens. So instead of doing this, I'm gonna do maybe I should add yeah, let's do that. So if then greater than 0, we do the transmit. That way I can use this helper function to just write a single command or single instruction, sorry. So 35, 0, basically 0 and 0. That should be fine. So let's do that. And flash it. Oh, this doesn't look good. Why? Line 245. Okay, so this actually failed. Why? Oh, could it be that I have to do this even with empty data? Invalid parameter. What about... No. I don't quite understand this. I mean, I can actually check out what's going on here. Because here we do that same thing. We set the command, or we just execute command twice without any transmit. And that's essentially what I'm doing here. This doesn't make sense. Okay, so it is in the OX4 state. What does that mean? Command configured, ready for an action. How do I finish this? Oh, this is beautiful. So if your length is 0, it will read the first byte anyway and decrement the buffer or the transfer count. Nice. Okay, I don't understand this HAL. I simply want to send a command without a payload. But it gets stuck in the incorrect state for some reason. Am I doing something wrong here? C flash reset. Yeah, and I'm doing that essentially, right? I'm doing the HAL OSPI command, and that's it. So if length is 0, I don't configure any pointer, and the length is 0, right? So what's your operation type? It should be common configure, right? Yeah. Set length to 0 if you're not. Yep, I'm doing that there. No, it's fine. I'm just trying to wrap my head around why this doesn't work. Like, let's just send it 3 times after each other. Because the issue is that data mode none. Oh, thank you. I think that might be the bug. Yeah, there we go. Thank you. Then it's bigger than 0. Oops. Yeah, that must be the issue. Thanks for pointing it out. Okay, now we can try it again. I'm just going to read the chat. For now, I wouldn't bother with Spi mode. XIP mode is basically the same without messing with the rest of the code. Yeah. look at this, we have data. Question is it the right data? Let's do a quick look. 80 to A. Okay. 80 to A. Yeah, it's the correct data. Sweet. So let's telnet and make a new dump. Call it 4. So this is now using QPI. Still not super fast. But right, this is limited by the debugger. You should finish the stream with some SMP3 uploaded with the code. Yeah, well, I'm not sure that's a good idea. Yeah, look at this. It works. So now we have proper QPI mode with 4 instruction lines. So this is like the fastest you can get. Nice. So now the real question is, what happens if we soft reset the device? I think it might break because all the commands we're sending will be interpreted as QPI mode. So maybe what I should do, which is kind of hacky, is to reset. I mean, one way is to send the QPI disable because it's a very short command. So even if you're in SPI mode, it will just be garbage for the flash chip, right? So we can actually do that in this function. Let me just use this one. So I kind of want to rewrite this. This gets ugly, sorry. Cool. This should work. So the question is, what is the command for that? That is F5, okay. Sweet. Let's try this then. Oh. Okay, it seems to work. Just gonna make a note out of this. And let's power cycle the device. Yeah, it's the same. Cool. Okay, so now the color test is to program it again. Actually, nice to see the work going forward on the Game & Watch. So if I understand what's going on, you just need to plug an SWD debugger, like an ST-Link, to program the flash. That is correct. And what I'm especially working on right now is support for the 128 megabit flash. This one. Because it is giving us more storage. But the thing is, it behaves a little bit differently from the other chip. So that's why I am doing this. So ideally this code should work with both chips, but we were sort of relying on sort of accidental behavior on the other one, I think. So let's go back to main, remove this, and enable the flashing. Right. I think I will, I don't know. I'm thinking if I should rewrite the code a little bit so that we have like a global state, which is the quad mode, if it's on or off, would be nicer. Actually have an enum for that. Starting to get annoyed. Right. There we go. And then we can rewrite this code a little bit. Oh, we should export this. Right, so yeah, a TFMOE, that was the case before. And until, like the bootstrapping problem is a little bit difficult, but we're working on that. So getting from a factory unit to what I have here without having to access the flash, that is sort of the goal. That would be really nice. Because what I have now is like I've already extracted the flash and so on, so I don't have to care about that, so I can just go crazy. But yeah, whatever you do, don't use this flash loader on a factory device because it will wipe the internal flash. Well, you need to explicitly change the RDP level from 1 to 0, and when you do that, it will wipe the internal flash. But you don't want to do that. You want to extract the internal flash first. But in order to do that, well, it's a little bit convoluted. So yeah, but be patient. In a few days, maybe there will be something. So what I'm doing now is that I'm rewriting it a little bit. So whenever you start it, we will attempt to disable quad mode. By the way, was it verified whether all the Game & Watch have the same flash contents or not? Yeah, so it's mostly the same. The bulk of the flash is the same. And then there are 2 pages or 2 areas in the end of the flash that are unique per device. But it seems that that contents doesn't really matter. Because what I did, I took the flash from one unit and put it on another unit. And it still worked with the stock firmware. So I honestly don't know what's that all about. It's really strange. I don't get it. Like, it doesn't make any sense. Yeah, okay. Yeah, I also have one extra unit that I haven't even opened, so it's like pure. So it would be nice to try out like whatever tool is coming on that completely brand new unopened device, so we know that it doesn't break. Yeah, Black Magic. Can't wait to see how you did that. Yeah, stay tuned. There should be some regional difference. Oh yeah, that is right. That is definitely right. Especially regarding the whole subtitle. Wasn't the subtitle wrong for some language? Like it was flipped. Like Spanish was French or whatever. It didn't make sense. Yeah. I'm just gonna step through the code so it makes sense. So I'm just gonna try it with the SPI mode. And all right. That didn't work. Guess I messed something up. So maybe the device gets sad if I do this. So I'm gonna... Oh, that was too bad. Okay. Guess I messed something up for real. Oh, right. Okay, that works. And if I add the delay or disable QPI mode, let's see if that still works. Okay, so just to explain what I just did, I rewrote it a little bit. So you start off by calling reset with a desired SPI mode. In this case, we want a single SPI mode. We send a disable QPI mode in quad mode, which will be only a few clock cycles wide. So if you're in SPI mode, this will not do anything to the chip. Then we enable reset, we reset the device, and then if we want to, we enable quad mode. And then in the other functions, we use this. All right, we also need to do this. Cool. So let's see if quad mode actually works. So just to verify that we're in SPI mode, I'm just gonna read a few cycles, and we can see, yes, this actually seems to work. Yeah, that looks fine. And then now I'm gonna try the QPI mode. Quad mode. That also seems to work. Does it look sane? Yeah, this doesn't look like anything to me, right? Because we can clearly see that we get data on multiple lanes at the same time. So this is actually quad mode. So now the real question is, if I want to enter SPI mode, what happens? Because I haven't power cycled the device, so I'm just going to do like this. And yeah, it works. Okay, so now it's confirmed. Now we have actually a proper way to initialize the chip in either SPI or QPI mode. Cool. So now let's try programming in quad mode. This is going to be interesting. So write enable. We should change this code to use the write bytes. Let's do that. So here we only use, we call the OX06 instruction, and we don't care about anything. So let's do that. And then we have the, right, and then here we should use that one, because now we can be in either SPI or QPI mode. Then we have the chip erase, which yeah, it does basically the same thing, it just sends commands. What about USB hardware mod for uploading firmware for microcontrolling content for SPI Flash? Yes, very good suggestion. I like it, but it requires a good soldering skill. And also, the native USB PHY is multiplexed, unfortunately. So the chip has real USB PHY inside, USB device, somewhere. I guess I can't even enable it because the tool knows that it cannot, or this is middleware actually. USB. Why can't I find it now? There is definitely a USB PHY. There we go. So if I try to enable it, it will complain because the pins are used. So you see here, the LTDC conflicts with it. So LTDC is the display. And I don't know exactly the pin right now, but one of the pins for the display is also used for the USB. Which means that if you want USB to work, here we go. So this pin is used by the display and USB. So if you connect a wire from the USB connector to this pin, yeah, it could work, but you cannot use the display and USB at the same time. And also, even if you write like a bootloader that only does USB and doesn't use the display, then maybe you will get problems because the transmission line is connected to the LCD, which might interfere with the signal. So that is annoying. Really annoying, unfortunately. Alright, so write enable was done, and then we do the chip erase. Yeah, let's do that the same way. OX60, and then we wait for the write in progress. Yeah. Alright. And let's adapt the program to be QPI or SPI. So I already had this here. We can copy it will always be set. So let's just do this. Does this make sense? Instruction mode. 4, 1. So now we need to find the quad program. Page program. So I guess it's the 4pp command. PPQ apparently. All right. So this is confusing. It seems like these commands can only handle a single data or a single instruction line, even when in quad mode. I wonder if that is the case though. I honestly don't know. Or maybe O2H can work when in quad mode. I have to try this out. I don't know. Yeah. Yeah, look at this. So this is interesting. So this is such confusing. So when you're in quad mode, you can use the SPI commands in quad mode. So you use the old O2H command, but send the instruction on 4 lines at the same time. Cool. Let's do that. So we keep this O2 and then we simply write it on 4 lines. Yeah. And dummy cycles. Yeah, that was 0, right? Yeah. Okay, cool. So this looks good. Oh, this might be. I think I need to change this. Yeah. Just use the same auto instruction if you're using QPrimer. Yeah, thanks. I honestly I've never had to set up this kind of thing, so all of this is kind of new to me. Because usually the low-level Flash stuff is sort of taken care of by someone else when you work with stuff. I don't know. For me, it's been like that. Like the really early bring up stuff is usually all the fun has already been done whenever I start working with something. So this is a learning process for me as well. Yeah, this we can try this, see if it works. So just to step through the code again, we do the reset, where we just write bytes. Then we do the write enable. Write enable simply writes using whatever instruction and mode. Yeah, looks good. And then we do the chip arrays. Yeah, let's do the DD and then run the script again. So time for a new random image to be sent. And this time we are using, oh, though I didn't change. So this is using SPI mode. Well, we can still double check that it still works. Yeah, so now we wait until the screen starts blinking. Okay, dumping it. So again, this is in Spi mode, but with the updated code. So in case I broke something, we will see that now. And it's the same. This is good. So I haven't broken anything. So let's try quad mode. Actually, this time we can just skip the flashing and just see if the readout works. That is still interesting to know. So now we're reading in quad mode. I think the ST-Link is operating at like 30 kilobytes per second or something. It's not very fast, but it's okay. We don't need speed. Nice, it doesn't differ. So now we should try to make a new random file and see if we can upload it. All right, I need to quit that one. So if this works, then I can commit this and we're done. Almost. So the big problem with this code is that we load the full image into RAM, which is only 1 megabyte. And the flash is 16 megabyte. So we need to do this 16 times and have an offset here. So I have to improve this a little bit, but we're getting there. Okay, it's blinking. So let's do like that, and then telnet, dumping this to 7. Okay, let's diff. Ah, look at that, it works. So this is proof that we can erase and program and read in quad mode on the big flash. That's perfect. I'm just gonna clean this up a little bit. Actually, before I do that, I'm gonna try with the stock flash and see if that still works. So let's see if this works. Then I will make a new image and flash it. So now I inserted a stock flash. So this flash is only 1 megabyte big. And I just want to make sure that I haven't broken the code. Okay, so now we're waiting for it until it blinks. Finally, a way to fully texture Doom. Yeah. Definitely. I mean, I think so. um, yeah. So the biggest downside is that this is painfully slow with this debugger, because this debugger is it is pretty slow. But it is what it is. It's better than nothing. It works. So for speed, you will need a faster debugger, or find a different solution. So, I mean, this is not like, like the end result. This is just a way for us to develop faster. Because previously, what I did was that I used a Glasgow, a different PCB, and I removed the flash and I inserted it here, and I used this hardware to program the flash. So every time I wanted to update the code, I needed to remove this, insert it here, run a command, wait a while, and put it back in. I did that many times. So I mean, sure, it works, but it was painful. So this way is way nicer. Okay, it's not blinking yet. I think it's a little bit slow. I don't like that. I don't know why it's so slow. It could be that it's stuck waiting for a result. Damn it. I am gonna halt it. And so this doesn't look good. Why are we stuck here? We're waiting for the register to update. Does stock flash support QPI mode? This mode is very vendor specific. Thank you again, Gorgo. I think yeah, thank you so much for letting me know. I completely didn't check that. I should check the wiki. Right. So what did I do to enable quad mode? Oh, right. I'm sending OX35. Damn it. Okay, so it's not 35 in this. Of course it isn't. Okay, this was stupid then. So I guess I need to refactor the code a little bit so that we can have different flash configurations. I thought I was done. I was not. I mean, I cannot find the command for going into quad mode. There is a performance enhance mode. Okay. I think it's simply different. So, okay, I'm gonna, god damn it. Oh, this is gonna be annoying. So if we're using the large flash, we can use the quad mode, but if we're using the stock flash, we need to use the specific quad commands, which work differently. So, yeah, well, it's not that bad. It's just code. It's just annoying to write. So we can start from the scratch. So let's go to the beginning. Reset. Okay, let's first of all just see if SPI mode works, because it should. Because that doesn't make any fancy stuff at all. Yeah, there we go. All right. WinBond uses 38 for QPI mode. Okay, but why don't I find that? Oh. Right, so this is actually the hybrid style. So the command is issued in SPI mode, and then the data comes in, or address and data comes in quad mode. So this command is just a mess. Yeah, thank you. I understand now, because I remember you wrote something before that was basically, oh, don't bother with QPI mode, it's a mess. And yeah, you're completely right. Why didn't I listen? But I had issues with the normal command for some reason. Anyway, let's just refactor this a little bit. So let's rename this function, call it USPI init. And we have quad mode, and then we have SPI chip vendor. And WinBond, I guess. But this is not WinBond, this is Marconics. Okay, so let's call it MX. And then we have ISSI, right? Stock flash is Maxnomic. Marconics. Macronics. All of these names are confusing. Anyway, this is okay. This is for this one. Cool. Okay. So maybe in order to make this less awful, I'm gonna move these down. And do this programmatically. So if quad mode is SPI mode, then we just do vanilla commands. Else we're in QPI mode or quad mode. We want to check if vendor equals MX. We do something. Else we do something else. Okay, sounds reasonable. So instruction is one line, data is one line. If we are in MX, instruction is one line, data is 4 lines. And here we do it with 4 lines. Right? This makes sense. Okay. Should I break this out into a function, or will that make it more unreadable? I don't know. I'll do that. Wait, set Okay, does this make sense? So now I can reuse this function everywhere, wherever I need to do this kind of stuff. Nice. Actually, I should do like this instead, because then I can reuse it and yeah, in another place. I think in reset I will need this. Winbond EF. Okay. Oh, right, this is not Winbond, this is Macronix. Right. Cool. Anyway. So, now this is nice. And then we can skip this and this. Oh no, damn it. Are you working on adding a larger flash memory chip? Yes, that is correct. Add support WinBond, please. Yeah, I could do that, but I have to work on in the blind because I don't have WinBond right here. But basically, this function will be like the important function, I think. Then you can just add another vendor here and it should be fine. Could micro SD card over Spi mode be an option? Yeah, honestly, I don't have any experience with micro SD, so I can't really answer that. But if I understand micro SD correctly, you can run it as basically an SPI peripheral. I don't know, but you basically need to improve this function where we send commands for every byte you read and so on. But honestly, I don't think this will work. You probably need to have like a driver, proper microSD driver. The nice thing with this is that you get the memory mapped directly. You get the memory mapped area directly to the SPI flash. So whenever you need to access, you can just randomly read from that memory. You don't need to do any setup. You just read the memory and it's done. No preparation, no commands and so on. It just works magically. It's super nice. Okay, let's see what we did here again. So data 4 lines. And here we should have 4 lines. This one. Okay, this is more like it. Yes. And here we have no address, but we do have data. Yep. What size is the flash chip you're installing? 128 megabit. So I have 2 chips here. This is a stock from Nintendo, and this is the big one. Okay, let's continue. So when I read bytes, I have the instruction. I don't have an address, but I do have data. Yeah, that's correct. And here, let's see what we do. We don't have an address, and we I think this should work, right? So if I do have a length, then yeah, then the data mode will be set. Yeah, that should work. And here we use both address and data, always. Oh my god, I saw another guy using 8 megabit and I thought that was big. No, okay, so just to be clear, 128 megabit and not megabyte, just so there is no confusion. So this means 16 megabyte. this should work, but it doesn't compile because I missed something. What did I do? Ah, semicolon. Now something else broke. Right. Okay. So let's still larger than 8. No compatibility issue. Well, that is literally what I'm doing right now. Because of compatibility issues, I needed to write all this code, which sort of makes it work in different ways depending on the vendor. So let's go. So what am I doing here? I am going to, well, I'm gonna try reading first. Okay. So debug and dump. Okay, it's probably erased. Cool. That's good, I guess. Okay, all right. So Spi Mode, vendor MX, and I'm using the stock flash. So when this works, we can try it in QPI mode. So this will take a while. Still 1 megabyte over SWD. So it's flashing now. And it's blinking. Okay. So we can halt and we can telnet and we can dump the image. I am kind of eager. I want to look at this. Okay, there is definitely data. That's really nice. Cool. Yeah, I have a good feeling about this. Let's see if it works. It's done. And now we diff it. And it's perfect. Okay, we have a perfect image. Nice. So this has, now we have verified that after my rewrite, we can erase and flash, and we can read. So now I'm gonna try it in quad mode. And make a new random file. Let's see if it works. Yeah, this is going to be interesting because if this works, then I think we have a nice piece of code. Yeah, but you're right. If you look at the U-boot, for example, holy crap, there are so many different configurations for various flash chips out there, especially for NAND flashes. They are not fun to work with. Cool. And if you have any feedback, like anything you want to say, just write it in the chat. I try to read everything. So it's still flashing. We are in quad mode, but it's not done yet. Even NES library alone is way bigger than 16 megabit or byte. Well, I don't know where you... What do you mean? JTH, do you mean like a lot of different ROMs, or... Because we have NES running. I can try it later. Game Boy Classic compared to NES is enormous. Okay. Yeah, I don't know, but Stacksmashing got Game Boy working as well, so I assume you won't be able to run the original Nintendo firmware from a larger chip. No, so the thing is, it is possible to get working by binary patching the original firmware to add support for the new Flash, but why? Like, I can understand why people want to use the original firmware, but it's just so much work. You need to reverse engineer that firmware, and because it patches the ROMs, so it doesn't work with any ROM. So I just don't. I won't have the energy to do that. Maybe someone else in the community want to do it. Go ahead, fine. But I won't do it. NES library has the size of all ROMs existing. Oh, holy crap! Yeah, that. Damn, that's probably a few kilobytes. Maybe a few hundred megabytes. I don't know. Maybe gigabytes. All the different emulators will exceed STM Flash very soon. Yeah. Well, yes, you're right. The 128 kilobytes of internal flash is not really enough. So we have to store program code on the flash. And then we copy that to RAM. Like so. So we store program code on the external flash, and then it is referenced on the RAM. And then in the main function we copy this beautiful code. But yeah, what this does, it copies the code that is stored on the flash into the RAM. And then all the pointers and function pointers, they point to RAM. So that is how you can have more code than what fits on the internal flash. Okay, I don't like this at all. So the device has been stuck here, not blinking. I don't know what's up with that. So I guess it's time to debug. So we're stuck sending a command. Let's do that again. Okay. I guess we're stuck in the command loop. Right, we're waiting for the. Actually, this is different. This doesn't look good at all. So at some point it will be external code from Flash. Well, JTH, that is what we're already doing, but because the Flash is slow compared to RAM, we copy the code from Flash to RAM, and then we execute from RAM. And with external code, we need file system, so SD is inevitable. Well, no, not really, but you can do that if you want to. How many Game & Watch should we buy to have the entire NES library? Well, yeah, right. With the SD card mod, yeah, sure, you can do that, I guess. Okay, but I want to understand what's going on here. Why are we getting stuck? So all right, we're why? This is not good. Yeah, all the Game & Watch game would probably fit into original game. Yeah, maybe, yeah. I mean, the Game & Watch, they use... I mean, the actual Game & Watch, they use physical LCDs that are unique for each game, but with the emulator, you need an image, right? Like if images to illustrate the different physical sprites, so to say. So honestly, maybe it can't really fit that many Game & Watch games because of the images. Anyway, let's see what's wrong. So chip erase. That went super fast. How could it be so fast? I'm starting to think that this is not working. So by the way, have you checked whether there are zeros by hot patching? What do you mean? Zeros. If you if you write zeros onto the external flash, or if you write zeros and then encrypt those zeros, or JTH, I don't quite understand. You mean, yeah. So I actually did that. So I wrote 40 kilobytes of zeros. Let me post that link, because I did that. I did exactly that. There we go. I'll post it in the stream. There you go. So that code is a dump with only zeros. Okay, let's try this again. I don't like that chip erase is so fast. It doesn't make any sense whatsoever. So I'm probably doing something stupid. So let's go through the code again. Write bytes. Yeah, this is that one. Oh, right. No, I mean verify this against all FF to check whether there are zeros. Yeah, man. The thing is, right now I think I just write. I just have bad code. I just need to debug this, because the erase shouldn't be this fast. Let's step inside, see what happens. I made a typo. 2 typos. This is why you should never copy paste code, and I do it all the time. Right, let's alright, I don't have the probes connected. Stupid. Yeah, let's see if this works. Okay, this takes too long time. It's not supposed to take this long time. Annoying. So let's see what's going on. We are stuck in line 50, where we are right 164. So we are waiting for the status bit to become 0. Oh, this doesn't look good at all. So okay, I think I got it. So the issue was that my nice code, so to say, was a little bit too nice. So it turned read of the status registers into a quad read, which is not really correct for this chip. Okay, this works. Nice. So now let's see what happens if we go into the memory mapped mode and see what's... Yeah, this is no good. Yeah, I'm starting to lose focus now, I think. This became a little bit too convoluted. I was trying to make something nice, I guess. Does this make sense? This is getting a little bit annoying. Yeah, you're right. You're right. Yeah. But at the same time, I really want to finish this. I seem to lose focus. Damn it. Yeah, I don't know. Maybe I should finish the stream now. I really wanted to do some Mario stuff later on. I don't know. Okay. you know what? I'm gonna finish it now because I'm losing focus. So yeah, thank you everyone who have been here. It's been interesting, and I will definitely finish this up so we have a proper Flash driver, and I'll commit that. So until next time, and I think I'll probably stream again, maybe even a little bit later tonight. I don't know, because I really want to hack more. Um, so yeah, thanks again for hanging out. And I'm really bad at keeping times, so I'll probably just start streaming. Maybe tweet a little bit before, and it will be live whenever it's been live. So please just subscribe if you're curious, uh, and you can get a push notification when I go live, and you can hang out. So yeah, thanks again for being here. So yeah, until next time.